Section 1.3, slope field and existence and uniqueness theorem. So I'm going to do this in two separate videos. First of all, what's slope field, which is also known as a direction field? Okay. And primarily, the purpose of this section is sometimes it's impossible or it's very difficult to solve the differential equation analytically. So we need to get an idea how the solution looks like, or in general, solution curves looks like graphically. So what we do, we construct what is known as slope field or direction field. So to get an idea how the solution curves look like. So consider dy dx is equal to f of xy, where f of xy gives the slope of the tangent line to the solution curves of the differential equation, where it leads to determining the overall shape of the solution curve without solving the equation. So we like to get an idea how the solution curves look like, you know, the graph of the solutions without actually solving the differential equation using this graphical technique called slope field, which is also known as direction field. Keep in mind fxy is the slope of the tangent line to what? Tangent lines to the solution curves, at any point on the curves, right? So here's the deal. Suppose we'd like to construct a what? Suppose we like to construct a slope field for dy dx is equal to 2x. So I'm going to start with something super easy. We all know the solution for this differential equation is x squared plus c. Well, let's just say we didn't know that. So how do we construct the slope field? To construct the slope field, what you do, you select some random points on the xy plane. So I just so happen to choose these points at random. And then let's see now. Then what I'm gonna do is what? Find the slope of the tangent lines, which happens to be given by this equation, by substituting the x and y components of these points which I selected. In the differential equation. Remember, 2x is the slope of the tangent lines to the solution curves. So there is no y involved, so this guy strictly depends on what? X. So if you choose 0, 0, dy dx, which is the slope of the tangent line, is 0. So what we do, we kind of draw a flat tick mark here to represent 0 slope. 1, 0, so dy dx is equal to 2 times 1, which is 2. So at 1, 0, the slope is 2. So what does that mean? From 1, 0, you go up to and what? Over 1. Remember algebra classes? Slope was what? Slope of a line was rise over run, wasn't it? So from here, you go up to, but let's say 1, 2 over 1, and you draw this line. But instead of drawing the whole line, we just put a tick mark like so. Okay, so did you see what happened? I went to 1, 0. At that point, 1, 0, I drew the slope. So what did I do? I went up 2 over 1. I got this point. So here's the line. But instead of drawing the entire line, I just put a tick mark passing through that point. Now, at this point, -1, 0, so dy dx is equal to 2 times -1, which is -2 over 1. So at this point, I go down to what? Over 1. So I draw this line right here. But remember, I only need a tick mark, which shows the line goes through that specific point. So believe it or not, if you continue plotting these points, you're going to end up with something like this. Okay. And and something like this, and so on and so forth. You see it. So it looks like if I were going to follow these tangent lines to the solution curves and draws, some of the solution curves, this is how they're gonna look like. I don't know if you guys can see it. There they are. Do you see it? So those are called solution curves. Solution curves, right? And remember, the idea was you don't know how to solve this, but you and I, we both know dy dx equals 2x is really a simple equation. So if you just solve this differential equation for y, you get x squared plus c, and that's basically how the solution curves should look like. So the solution curves have the equation of y equals x squared plus c. So for every c, you get a specific solution. For instance, this guy is when c is 0, this guy when c is 1, this guy is like when c is -1, this guy is like when c is -2, and so on and so forth. Remember, this is kind of like general solution, which gives you a family of solutions, but the minute they give you what? Initial conditions, you get to choose one of these curves, not all of them. So this is basically how the slope field looks like. So what we do, we find the tangent line to the solution curves at each specific point, and then we follow the tangent lines to see how the solution should look like. So these are the solution curves for this differential equation. Remember, the idea was we didn't know how to solve this. So one of the problems which I used to give in classroom was this guy. The idea is, look, you got 4 equations and you got what? 4 slope field. Could you match equations 1, 2, 3, 4 with the slope fields A, B, C, D? And if so, how would you go about doing this? So the way we do this, remember the idea is you don't know how to solve these guys, right? You want to get an idea how the solution curves look like, based on pictures, not analytically. So here's what I did. I said, okay, let's take the first equation, which is what? Dy dx is equal to 3x squared minus 4x, this guy. Okay, let's see which of these slope field matches what? This equation. What did I do? I kind of, chose some random points like what? 1, 1, -1/2, 0, 2, 0. Let me just zoom in so you guys can see. 2, 0, 0, 0, 3/2, 1. Remember, what's on the right side is, remember the general equation looks like this guy, f of xy. So on the right side, you have a function of xy. So in our case, what? Our fxy happens to be 3x squared minus 4x, correct? So this is the what? Slope of the tangent line, what? Lines to the solution curves, at any point, okay? X comma y. So if that's the solution, so what I did, I selected these random points, 1, 1. So I substitute, notice the slope solely depends on x, so it has nothing to do with y. But remember, you have to choose these order pairs on xy planes. So this is not a number line. So anyways, if you replace x's with 1, you get 3 minus 4, which is -1. Slope is negative. For -1/2, 0, at -1/2, 0, slope is positive. At 2, 0, slope is positive. At 0, 0, slope is 0. At 3/2, 1, slope is positive. So if you go to this curve, that pretty much satisfies my conditions. Check this out. Suppose at 1, 1, so here's 1, right? And here's 1. Okay, what was the sign of the slope? It was negative. Okay, so that means I have to have this kind of tick mark. Do you see it? All right, at negative 1/2, so here is negative 1/2, what? 0. Here is, where is it? Here is 0, right here. Negative 1/2, 0. Negative 1/2 for x, 0 for y. I got positive slope, so there. Okay, that kind of satisfies that guy. At 2 comma 0, 2 comma 0, right about here, I came up with positive slope, so that's positive. At 0, 0, so here is 0, here is 0, I came up with 0 what? Slope. And finally, at 3/2, which is what? 1.5 comma 1, right about here, I came up with positive slope. So what I'm saying is select some random points, on top, left, and upper right, middle, lower left, and lower right, and see if the direction of the slope of the tangent line matches with what you have on your table. So the table which you end up with, remember you kind of ended up selecting these random numbers and you computed the slope of the tangent line off of the equation, differential equation, which is given to you. If you got all corners, pretty much covered, so you can tell, oh my goodness, this must be the solution, what? Slope field for equation number 1. So if that's the case, how would the solution curves look like? Well, they kind of sort of look like this. I don't know if you guys can see it. So this is how they look like. Do you see it? So those are the solution curves for this particular equation, even though I did not solve for y. But you know what? If you would have solved for y, that would pretty much confirm our findings. Check this out. Remember, we weren't supposed to solve. We were supposed to get an idea based on graphs or slope field. So dy is equal to 3x squared minus 4x dx. So if you would take the integral of both sides, y is equal to x cubed minus 2x squared plus c. Yep, that's about right, because the pictures of cubical polynomial happens to look like this, like a snake. So that kind of confirms it, even though I did not solve the equation, but yet I was able to tell how the solution curves look like via what? Slope field, or sometimes it's called directional field. One of the famous equations is Newton's law of cooling. Remember this guy? So the question is, if T, with Tm, which is the temperature of the surrounding, is 70 degrees, and K, the constant, is 1/80, can you sketch corresponding slope field and some representative solution curves? So once again, you select some random points, like let's say, I don't know, T equal to 1. And remember, T is the time, capital T is the temperature. Right about here, I'd like to know what the slope is. But remember, this equation has no lowercase t on the right side. It solely depends on the temperature of the body. So at 70 degrees, this guy is 0. At, let's say, I don't know, 0, 0, this guy is 0, so negative times negative is positive. So this guy is a positive. Okay. At, let's say, 0, 140 degrees, okay, if t is greater than 70, so this guy is positive times negative is negative. All right. If it is less than 70 degrees, which is the room temperature, let's say this guy is negative, negative times negative is positive. like let's say right about, I don't know, 0, -70, this guy is positive. So you get something like this. So because at time 70, which is the room temperature, this rate of change is 0, so we have this what? Dotted line. So this is in the land of mechanical engineering called equilibrium position, correct? If T is greater than what? 70 degrees, this guy becomes negative. So notice the tick marks are what? Pointing downwards. If this guy is what? Less than 70, the tick marks are positive because this quantity becomes positive. And lo and behold, if you follow all these tick marks as you might be able to do it, so you get these solution curves. Do you all see it? But notice they all, from the top and bottom, converge to what? 70 degrees, which is the room temperature. What does that mean? That means if the object in the room was colder than the room temperature, it would what? Eventually warm up to room temperature. If it was warmer than the room temperature, it eventually warms up to what? The room temperature. So 70 degrees is the equilibrium point, which means there is no rate of change here. The temperature does not change when T is exactly the same as the room temperature. Thank you.